In today's note, we're going to look at interpreting quadratic relations. So this is basically extending on what we did in the last note, except now we're going to be actually reading and understanding what the quadratic relations give us or tell us. So in example 1, we have the graph that represents the path of a ball where y is the height in meters and x is the distance in meters. So x is distance and y is height. So A, we want to state the coordinates of the vertex and interpret the meaning of the vertex in the context of the situation. So in order to find the vertex is the highest or lowest point. So in this case, our graph only has a high point, right? Because technically, if we know about quadratics from our last note, these lines would continue down in either direction. So we do have a high or a maximum value. So this is our vertex. So that means it has a point of 10, 9. So again, remember x, so go over 10, then up 9. So that's our vertex. So we're just going to restate it. The vertex was 10, 9. And what does this vertex actually mean? Well, there's two different ways we can look at it. They both mean the same thing, just one is more technical than the other. So the first thing, you could just say it's the highest the ball goes. So it's the highest the ball goes, which is 10 meters, or no, sorry, 9 meters. And the second thing, we could actually just interpret the point specifically. So you could say at 10 meters distance, the ball is 9 meters high. So again, treat this idea of looking at it as almost like a two-dimensional version of a person throwing a ball, and it travels up and then comes down. So for B, we want to state the x-intercept. Again, if we're not sure what the x-intercept is, it's the same as it is with linear relations. It's where the line or the graph crosses the x-axis. So if we go up back to our graph and look at the point where it crosses or touches, so it touches right here. So this is our x-intercept, and the point is 21, 0. X is 21, y is 0. So we want to state the meaning. Again, I'm just going to restate the x-intercept. The x-intercept is 21, 0. And what does this point actually mean? Well, again, if I go back up and look, sorry to keep moving up and down, but if I go back and look, the ball has traveled up and it comes down and then it stops. So basically this point, or this x-intercept, is when the graph or when the ball hits the ground. So when the ball hits the ground, again, we can get more technical and just say at 21 meters away, or 21 meters away, the ball hits the ground. So again, using the specific numbers from our point. Lastly, we want to look at the y-intercept. And again, the y-intercept, again, same thing as linear relations. It's where the line crosses the y-axis. So again, same as with linear relationships, it's no different. So let's go back up and look at the graph to find out where that point is and then interpret it. So if we go back up to the point, we can see here that this is where the point touches the y-axis. So this is our y-intercept, and it has a point of 0 and 1.5. So we want to interpret that meaning, And if I think back to the y-intercept for linear relations, the y-intercept meant the initial value. So again, it's still the same thing. So the y-intercept was 0, 1.5. So it's still the initial value. So the ball is 1.5 meters high before it is thrown. So that is what that point actually means. Or you could say again specifically at 0 meters distance it is 1.5 meters high. Same thing, just more technical. In example 2, we're going to look at the same thing, except we're going to have to come up with a table of values and then graph it. So we'll look at using Desmos to help us graph it, but let's fill out our table of values first. So we want to consider the diagrams of position 1, 2, and 3, and the table below represents the relationship between the position number and the number of tiles. So position 1, there are 6 tiles. Position 2, if we count them up, there are 12. And if you were to continue this pattern, position 3 has 20, position 4 has 30. You could look at or figure that out by seeing how much it increases by. So by 6, by 8, we see an increase of 2, so then by 10, and then 12. Or you could actually go through and figure out, okay, so it was 4, this was 5, and we added another row. So then the next one would have to be 6, and we would have to add on another row as well. So it would be 5 groups of 6. So 1, 2, 3, 4. So there's 5, and then 1. So there we have what position 4 would look like, and if we counted all of those up, we would see that there are 30. The squares are 30 tiles. So that's our table of values. In A wants us to perform a quadratic regression. And basically what a quadratic regression is, or what it means, is we want to basically just find an equation. And we're going to use Desmos to help us do this. So I'm going to open up a Desmos window in a second, but just for those that may not have it, again, you can download Desmos or open the app. Like you can use it or on your phone, or you can just go to the website. But the first thing what you're going to do is create a table of values, and then the second thing you're going to do, you're going to enter y1, a squiggly line, a x1 to the power of 2 plus b x1 plus c. And that will give you your quadratic regression. So let's set this up. So we're going to create 2 windows now. So we already have Desmos open. What we're going to do is we're going to create our table of values. So I go to plus, add a table, and I'm just going to enter my table of values. So the x values were 1, 2, 3, 4, 5. The y values were, were 6, 12, 20, 30, and 42. And you see that it starts to graph those points. The next thing we're going to do is now we're going to enter this equation that we just wrote out. So in a new box, we're going to start by, and I'll bring up this here. So this is what you would see if you had the app, and you'll see where to enter everything. And you can do the same thing with the keyboard. So we're going to do y1. We're going to do a squiggly line, so down here. And again, that's on your keyboard as well. It's above the tab button. You may have to press shift. then we're going to do, so we need ax1 squared plus bx1. So again, I'm not doing anything to make it subscript. I'm just typing in a 1 right after and it comes up. And then finally plus c. So that is how you get a quadratic regression on Desmos, and we see that we get the actual regression here. So basically we have our main function here, or this is the format, and the a, b, and c down here are what we have to fill in. So if I go back to my actual note, the actual regression or equation is y equals, a is 1, so I can just write x squared plus 3x plus 2. So all I did was I just took these values, the a value, and put it into the equation. So a became 1, b became 3, and c became 2. And that's this is now my equation for this specific table of values. So we're going to go back here, and for b, I want to know if it's at position 10, what is the number of tiles? So again, I could go through and I could make a new diagram for position 6, 7, 8, 9, 10, but that's just going to get very tedious. This equation is what I can use to help me figure this out. So if I have this equation, y equals x squared plus 3x plus 2, this position number here, this position number is basically just what x is equal to. So that is saying that x is equal to 10, and I want to figure out what y is. So that means in my equation, I'm going to substitute 10 in for x. So it's now going to be 10 squared plus 3 times 10 plus 2. And this is just a calculation I can solve on the calculator. And I get y equals 132. So therefore, there are 132 tiles at position 10. For C, it's the exact same thing. If the position is 25, what is the number of tiles? So again, this right here is telling us that x is equal to 25. And I have my equation. So I'm going to replace x with 25. So 25 squared plus 3 times 25 plus 2. And when I solve that on my calculator, so 25 squared plus 3 times 25 plus 2, I should get 702. So therefore, 702 tiles at position 25. So again, you can see why it'd be easier or better to have an equation to help us solve this rather than having to draw out each tile. So again, if you wanted to our graph here, if you really wanted to, you could on your graph zoom out until you found 10, or you can click on here and go up until you find 10. So if we keep going, so 10, we can see basically it's 132, and you could do the same thing for 25, but even that is a little bit more difficult. So sometimes it's just easier to get an equation and then substitute a number in to solve for it. But again, the main idea of this is just being able to understand how to use the equations to find information, and if you're looking at a graph, can you find key information from that?